Okay, then, yes, good morning, everybody. Good to be back. Thank you, Nestor, for soldiering through that voice of yours, poor guy. This lecture is about the dynamical theory, and I'm a metallurgist, as you know now. So all questions will be directed to Professor Darker here, who's the physicist among us, the wolf in sheep's clothing. So he's got it. So I know nothing about this topic, so we'll see how we go. And we're going to start with this very complicated diagram here that you know, bright field, dark field imaging. And okay. And a lot of the figures I'm using I've taken out of the Carter-Williams book, if you want to go and find them yourself, right? So you'll see them now. And that's why I've left these, the figure numbers on here for you. And the notes for yesterday's lecture and the two today, Nestor has them and he's passing them on their PDFs, so you'll get them if you want them. So anyway, you've heard about this from Nestor. It's not a problem then. And this mass thickness mechanism of observing lighter and heavier materials. We know about that then already. And then we talked about the Abel sphere yesterday and Bragg's law. I call it a geometrical theory of diffraction. And we can make a small angle approximation of that equation, and we had this yesterday. So you're all up to date on this, right? So that's good. Okay, we did that yesterday. The one thing we didn't talk about yesterday was this vector here, which connects, this is the zero order Lowry zone here, and say this is our, not necessarily a convergent beam, but say if we have a parallel beam with just one Abel sphere, this would be the deviation parameter between the diffraction event and the Abel sphere. And I think you already know from your classes that when we have thin foils, we have these railrods by these reciprocal lattice points that allow us to get diffraction when we're not exactly on the Bragg condition. Right, so, okay, so this is all good stuff from, and the other thing we can do is we know that we can orient our electron beam down zone, or we can then pick out what we'll call two beam conditions. And that's even though we've got other beams here, we still call this main, because we've got two major beams, the zero, the incoming beam, and then the diffracted beam in each of these cases. So we're deliberately tilting, and Nestor mentioned Kikuchi maps and so on. We're using those to guide ourselves around the sample crystallographically. One nice thing about these older fashioned microscopes is they have big tilting stages. And the fancy high-res microscopes don't. So a lot of what we want to do here is use an older microscope, and you'll be able to tilt around and so forth. So, all right. And again, this is I'll come back to this later on, and Nestor's already talked about this somewhat, that we can end up with things like exciting plus 3G here and looking in dark field, so we actually get this weak beam dark field. This is the strong two beam dark field, and this is normal imaging in bright field. And it's just by tilting the beam around that we get that. And that would be plus G, this would be minus G, and we have to note that as well. And then I just want to make sure I'm giving you the right lecture. I think I am. We'll go on. So this is a planar slip in Tie 6-4, and we have here this vector S. That's a deviation parameter. When it's zero, it means the Abel sphere is going through the reciprocal lattice point. And in that condition, you can see we get a sort of grungy kind of image. It's dark and so on. So that's at the Bragg condition. And then as we increase the deviation parameters, as you're getting greater than zero, you can see now that we start getting the some clearer images a lighter background, and our dislocations here are dark. This is in the bright field image. And if we continue to increase the deviation parameter, then we start to lose some of this, what I'll call the wiggly contrast. So these are images of dislocations, and you all know that dislocations have a thing called line tension. So it's going to be, they're going to resist the notion of being wiggly. They like to be straight. So something's going on in the imaging that's giving us a wiggly image when we've probably got a straight defect. And that's where the dynamical theory really comes in. And then this goes even much greater than zero. We start to lose then image quality. But you can see that what we've got now are almost straight lines here rather than wiggles. And all we've done is increase the deviation parameter. And so what we can jump ahead and say, okay, this stuff here is dynamical scattering, and this is more like kinematical scattering. So something in the dynamical scattering is giving us these wiggles and sort of fringy contrast. And so, and in fact, we like this because this is really quite an interpretable image, and this is, we're losing image quality here. So, all right, we're getting straighter defects, but we prefer to have the wiggles in terms of being able to do quantitative analysis of these defects. Okay, and then for stacking faults, we end up, say, we have an inclined stacking fault in the foil like this, and we're looking edge on here. And here's an image then, with the beam coming down. And you see we have a set of fringes here, bright to dark. And what do we notice about them? Sometimes we have bright fringes on the outside, and this corresponds to either the top, or the bottom, or the bottom of the foil. We'll see that we can actually determine that. And this is in bright field. In dark field, it turns out there's an asymmetric image. I'll have to show you some image profiles through this, because this is taking an image and then putting it under the presentation and putting it up on the screen here, and we lose detail. But I'll show you what's going on. But the interesting is, you can tell that this is quite bright, and this is quite low intensity here, right? So we have to understand where is that coming from? Why is that occurring? And why do we get the lowest contrast in the middle of the foil? Well, we'll get to that. So, and we say outermost fringe below background in this case. Okay. So we'd like to understand why we have symmetrical fringes in bright field between the top and the bottom, and where we have asymmetrical in the bright field, in the dark field image here. And again, we can't tell that from what I call the geometrical theory of electron diffraction, right? Just simply Bragg's law. Okay. So I call this the simple incomplete version. If I can press the button correctly. All right, so we have this. We know what Bragg's law is. And we can have a sample with a bend in it. That bend could be produced by dislocation, or it could just be a bendy foil. And we can say that the amplitude scattered ends up looking like this, where T is the foil thickness and S is the deviation parameter. And so we think, this is kind of looking like an important equation, so that's nice, a bit more complicated for us simple metallurgists. So we think we're on the right track. And this thing here is called the extinction distance. We'll get back to that. And interestingly, this says there should be a variation with the thickness and also with the deviation, with the orientation. All right, so this is now going from the edge of a foil, getting thicker and thicker and thicker, and we're predicting we're going to have fringes like this. Here are the fringes, so that's interesting. And then a variation with orientation from the S factor here. And we're looking here, we can see line there, line there, line there, line. It gets rather dark in the middle here, and then we come back to the other side. So we call this a bend contour. Again, it's just a bend in the foil. That's right, that's all it is. And here's the edge of the foil out here. But each of these is, Bragg 1, Bragg 2, Bragg 3, Bragg 4 reflections as we go out. So you might think that looks pretty good, that we can predict both the change with intensity with thickness and with orientation. Here's the rub. You notice that our fringes die out. So that could mean one of two things, right? The first thing it could mean is we've got a variation in thickness that becomes constant, and therefore we don't really get any fringes. Right, so we're getting thicker and thicker and thicker, and then we're not getting thicker after this. So that means if you're a defender of the geometrical theory, you're going to say, haha, that's what we have. But actually you don't, because when you make a thin foil, it keeps on getting thicker. So we're losing information here that we can't explain by the geometrical thing. And then here, if I were to take a profile, intensity profile from the middle here, which will be the symmetry position going out, when I go through the first maximum here, which is the first dark thing, I have something like this. So my rocking curve would look asymmetric about the Bragg condition here. Why? That's not predicted by the geometrical theory either. So if we look at this equation, it turns out that if we exceed this number here, if the thickness gets thicker than this, then we start making electrons, which is extremely naughty, and you're not allowed to make electrons, right? So there's something wrong with this, and it says that the kinematical theory, what I call the geometrical theory, is valid for very thin foils. And when we start getting any reasonable thickness that we want to look at defects and so on, then it's not really valid. And therefore we have to, whether we like it or not, because we don't like complicated theories, but we have to think about dynamical scattering. We need a more accurate description, and that's the dynamical theory. So in the following, I'm going to go through some equations that if you're like me, your eyeballs will start rolling. But don't worry about it, because you can read it afterwards, and most of you probably know more about this than I do, right? Because you've had good physics at this university. And so let's go, because I'm not doing this to try and confuse you. I want to do this to try and lead you to the point that you understand why we get things like this asymmetrical rocking curve, and why we get dying out of fringes, why we get wiggly images, and so on. And we can understand that from this thing. So assume that our electrons are incident on the foil in the form of a plane wave. And if we do that, then we have a plane wave like this. This is our wave vector, chi is our wave vector, mass electron, charge electron, and Planck's constant. You all had that before. And what we can do is to solve what's happening to the electron wave in the crystal, we can apply Schrödinger's equation. We can get a solution to Schrödinger's equation. And those solutions exist, so we don't have to make that up. We don't have to sort of work on that. They just exist. So Schrödinger's equation looks like that. You've seen that before, and all of you have, because you've done physics at this prestigious university. E, in this case, is the accelerating voltage, and V is the crystal potential. So our plane wave is going to come in, it's going to enter the foil, and what's it going to see? It's going to see the crystal potential, right? Which happens to look a lot like atoms, spacings, right? So, of course. And so, we know what the accelerating voltage is, but for this crystal potential, we're going to simulate that with a Fourier series, and we're going to make it look like this. And I'm going to do the usual thing. You all know what these things are. So we had for the electrons outside the crystal, from the previous slide, this expression. And then inside, the periodic crystal influences the plane wave. So this is our plane wave here. And then we're modifying that by this function here, which is called k. Or k is the wave vector inside the crystal. Chi was outside, k is on the inside. And this is the plane wave. This is the block function here. The block function looks like this. So it's a periodic function. That's where we're getting the periodicity from. And so we can then go back and say, right, our wave function inside the crystal is going to look like this. And then we can do some rearranging, and so there it looks like that. So here we have an amplitude term. Here we have our wave vector. G is to do with our diffracting planes, as we think, but it's to do with the crystal potential. and R is the positional vector. Okay, so this is a Bloch wave. So this is one of them in the solution. And in fact, in principle, there's an infinite number of them, of these Bloch waves. So, incidentally, we love Bloch waves, as you'll see, because they tell us a lot about the things we want to know about. So, this is the ith Bloch wave. It has an excitation. To what degree is this Bloch wave excited? And that's that term. This is the amplitude of the ith Bloch wave in the given beam, so either direct beam or the G, 2G, 3G. And then here's our wave vector for that Bloch wave. So you can imagine already that our excitations will vary from one Bloch wave to the next. Our amplitude will vary from one Bloch wave to the next, the way that Bloch wave is distributed across the diffracted beams. And we're going to have a series of wave vectors for each of these Bloch waves. So when you have wave vectors, i.e. related to wavelength, and they vary just a little bit from one of these Bloch waves to another, what might you expect? You might expect some interference effect, right? So, like a Doppler effect, right? And we're going to see that plays a major role, right? So these three terms are very important. I think excitation. So that's the excitation of this Bloch wave. CG, for this Bloch wave, this is how the amplitude of this Bloch wave is spread over the various diffracted beams and direct beam. And then our wave vector, wave vector. Okay. And this is all of the ith Bloch wave. So to find a solution, we need to determine the values for the excitations, the amplitudes, and the wave vectors. And that's what we're going to do. It won't be so rigorous, so please excuse me, but I want to get to the point where it's something useful for us, each one of these, okay? All right. So the first thing we want to know is, look, we know, when we look at a diffraction pattern, that we have a direct beam, we'll have a diffracted beam, first order, second, third, fourth diffracted beam. We know that because we see it in the diffraction pattern. But what's the relationship with these Bloch waves? So is there a relationship between them? Of course there is. So there are in principle an infinite number of Bloch waves, but usually there are only a few that are strongly excited. That's the theta term. All right? So there are only very few that are strongly excited. And, naughty, here we go. There are also an equal number of Bloch waves as there are diffracted beams. So you know when we said we had two-beam condition, because we could see the direct beam in a strongly diffracted beam, even though there were little ones around there, but we said that's a two-beam condition. Well, that's exactly what we'd have. We'd have two strongly excited Bloch waves, and there will also be Bloch waves corresponding to all these other waves. But what is the relationship between them? So here's a thin foil, here's the incident beam, and here is a direct beam, diffracted beam, a second diffracted beam, and so on, right? So that we know that because we see that in the diffraction pattern, right? So that's not a problem. We don't see Bloch waves, right, with our naked eyes, so we're a bit skeptical, right? So where are they? So they're here. So for the first Bloch wave, there is an amplitude of that first Bloch wave in the direct beam. There's an amplitude of that Bloch wave in the G and 2G. So the Bloch waves exist in each of these diffracted beams. So that's how they're spread. So we can also say, okay, there's what we just saw, but actually there's going to be in this direct beam contributions from the first Bloch wave, the second Bloch wave, the third Bloch wave. And each of those is going to have a way that it's got spread across the lattices. Across the diffracted beam, sorry. refracted beams. So when we want to say what's the intensity in the direct beam, we're going to add up all the contributions from the Bloch waves, but just their C0 contributions. And each of those Bloch waves will have slightly different wavelengths, because the Ks will differ just a little bit. We'll see what that means shortly. Okay. So this is the metallurgist saying something. Substitute that and that into the Schrödinger equation, yields the result. So don't question me, because it comes right out of the books. So there it is, and you'll see a lot of this you'll have seen before. Maybe you won't realize it's as useful as it is for us here, but we're just going to go through this quickly. So there's k squared equals this. That's chi squared. Remember, chi was the wave vector outside, plus this, and this is the mean inner potential as the electrons enter the sample. So it's like a refractive index effect. So k is the wave vector of the incident electrons after correction for lambda due to the mean inner potential, right, that U0. And so it's a refractive index effect. And we're going to make our 2-beam approximation. So how many Bloch waves are we going to have? 2, right? So for the direct beam, our equation will look something like this. And you'll notice we have 0 here because it's the direct beam. And also, you notice that we're going to end up by summing them over I here. So that's because we're going to have 2 contributions to there, right? So from each of the Bloch waves. And so we write this. This is standard dynamical theory type stuff. And so now we can get equation like that. For G equals G, we're going to end up with a different set here because we've got K plus G. And these are the wave vectors of our Bloch waves. This is the wave vector of the electrons when they've entered the foil, but they haven't yet started interacting with the crystal potential. All right, so then we can make this matrix equation, and then we can multiply that out. It's going on strike here. So we can multiply that out. And just to remind you of simple trigonometry, or remind myself of trigonometry, and the high energy approximation that our wave vector of our Bloch wave is very much like the wave vector of our Bloch wave plus G, and also of our wave vector K. They're all about the same value, slightly different. So we can then rewrite this equation here like that. Those are 2 Ks. So we can end up with our 4K squared there. And outside the crystal, K is equal to chi. Inside the crystal, not yet interacting, large K is chi squared plus the mean inner potential. And then when they're interacting with the crystal potential, which is when we get our small k's from our Bloch waves, then it looks like this. Right, so bear with this just for a minute. The quadratic therefore has 2 solutions. Quadratic. So each of those is a solution for little k, basically, so we have 2 Bloch waves. So we've gone through an approximation of the mathematics and ended up with 2 Bloch waves. So let's introduce our dispersion surfaces. You all remember this from your physics, solid state physics, right? So this is just so here's a dispersion surface, basically. So these are all for low energy electrons in the crystal. But we have this wonderful electron microscope which is producing very high energy. And so when we go to high energy, we end up having to go further out. And these are the interactions. This is the dispersion surface that we're interested in. And if we blow that up, it looks like this. So way down here, these are the wave vectors here. This is chi, this is K2, second Bloch wave. I haven't drawn in the other one for the first Bloch wave. But here we have, this is where, for this orientation, this is where we have the wave vectors for the 2 Bloch waves. And remember what we said we wanted to do was find out about the excitations, about the CGs, and about the wave vectors. So this is about the wave vectors here. They're shown on this dispersion surface. And of course, as we vary orientation, we're going to vary like this. So these will go out like that there, and out like that there, and be closest there. Okay, So at Bragg, that's where our dispersion surface will be. So our block waves would have k vectors here and here on that dispersion surface, on that dispersion diagram. And these red lines would be the capital K, that's the wave vector of the incoming electrons after they enter the crystal, but before they start interacting with the crystal potential. And so these are the Ks, the block waves, when we are interacting, of course. And that's with a positive deviation from Bragg. And so we had that. We'll play with these. And you'll see we're going to put a lot of substitutions in here to keep things fairly simple. So this is K squared there from the high energy approximation. So that's now our equation relating K. And so now we're going to, the first thing is to define this vector gamma. And the gamma is going to equal K minus K. And if you remember that diagram, I'll show you now. That's the diagram there. So there's our gamma 1 and gamma 2. Gamma 1 for the first block wave, gamma 2 for the second block wave. And we're just describing that because it makes it a little simpler to do that. So gammas are now a representation of these the wave vectors, right, for the block waves. So for g equals 0 and g equals g, the left-hand side of that previous equation becomes that. And you can read through the mathematics if you're really interested. But the k minus k is just minus gamma of I, and we have k plus k is just 2k. And so that's that. And we can write that equation we had previously like that. And that's gamma 1 plus k minus s of g. S is that deviation parameter. So it simplifies to that. When I say simplify, it means it's got less terms, right? So it might be more difficult, who knows. Right, but this yields then for our matrix equation that, or just write it in this way. So remember, gammas here are related to our wave vectors of the block waves. That's the description now that we're using. So we end up with this equation, blah, blah, blah. And I want to get to a result shortly. So you can work through the mathematics. In fact, please find some mistakes. And for these, from this equation, we can just obtain this, and that's simple mathematics to get that. So at Bragg, so when SG is 0, this becomes gamma I is UG, plus or minus UG over 2K. All right, so then gamma 1 minus gamma 2 will end up equaling 1 over the extinction distance. And you know the extinction distance is going to have something to do with the periodicity of these fringes that we've seen in the images. And so this, at this deviation from Bragg, this would be 1 over the extinction distance. And obviously at Bragg, I think I'll go to Bragg next. Yeah, at Bragg here, this would be the 1 over the extinction distance here at the Bragg condition. And so we can see that the extinction distance is at a maximum at the Bragg condition and will decrease with change in orientation from Bragg. So if you take your foil, your thin foil, with these fringes, thickness fringes we saw, and you were to orient the foil to the Bragg condition, that would say that the extinction distance is at a maximum. So there'd be a certain periodicity of these things. If you then started deviating from Bragg, they're going to start running up towards the surface because now the extinction distance is decreasing. So this is a visual, at least consistent with this notion, a visual proof of that. That's why. And you can't explain that by kinematical theory. Oh, sorry. So the thickness fringes observed are a consequence of the beating of two block waves, each with an individual value of its wave vector, but with only a small difference in these values. Now we still have the problem that we're losing intensity here as we go thicker into the foil. So you've got to get back to that. Why is that? So we had that. So again, we can run through some of this mathematics. I'm not going to stop. You can read through these in the notes if you're really interested. That little k minus big K is gamma and that is 2k from the high energy approximation. So we end up with this equation. So now we're doing another substitution. We're saying let's have a deviation parameter w. There will be the s that we saw. That's the deviation from the evosphere from the diffracting condition, the diffraction point, and our psi g. Okay, so we call this the dimensionless deviation parameter. So we had that. You go back in the slides. So we can now say that our CG1, so now we're looking at CGs here, trying to get some idea how these values vary, will equal 2 times the extinction distance times gamma 1 there. So that's the first block wave, and that's the ratio of the amplitude of the electrons in the G diffraction vector or in the direct beam. And that will actually become that. So we end up with this equation. And that's why they've made this substitution, because now that looks kind of easy. And then they have another substitution. They let beta be defined as W equals cot beta. And since we know that the square of the amplitudes, and add that for the direct beam and the diffracted beam, will be 1. This isn't a 2-beam approximation, right? Will equal that as well. Then we can say, using that expression, we can end up with, substituting those three arguments, that's why I named them A, B, and C in the previous slide. We end up with this as our solution. So this is the amplitude in the direct beam of the first block wave, and it's equal to cos beta over 2. And this is the amplitude of the first block wave in the diffracted beam, and it's equal to this. And here we have for the second block wave, we have the amplitude in the direct beam is this, and for the second block wave, the amplitude in the diffracted beam is that. Okay. So the amplitudes of the given block wave in either the direct or diffracted beams. So remember, that's our relationship. So here we have two diffracted beams. We have 2 block waves. And so this is the C0, and that's, of course, the wave vector. And this is the CG. And there's, of course, a contribution from the first block wave and the second in each of these. And that's repeating what you had in the previous page there. So that's what all this means. That's our values for the CGs. So we've got the Ks, we've got the Cs, and how about the excitation parameter? The theta to the I, or the I, it's the ith. Right? Of course, we're just going to have 2 in this case. So these are determined from the boundary conditions. So the amplitude of the direct beam is that. The amplitude of the diffracted beam is that. So we end up with the direct beam at 0 here, which means at the surface, incoming surface, we haven't gone in yet, will equal this, and it'll have a value of 1, the excitation, the phi, and this will be 0 because we haven't diffracted yet at all at the surface. And so we can write this matrix equation from that. So use the diffracted amplitude, C is the eigenvector matrix, and theta is the block wave excitations. That's what we're after. So at Z equals 0, here's our matrix, and it has just one value in it. So we can write that, and so we can say that the amplitude of the ith block wave would equal the amplitude of the ith block wave in the direct beam. So we've already got that knowledge of that, so it tells us, therefore, the excitations are given by the amplitude of the given block wave in the direct beam. So now we've got idea of each of these 3 things. Let's see what's going on here. So theta 1 is that, theta 2 is that. Oh, and of course, it's important to know excitations vary with orientation, right? Because beta is a orientation parameter. Okay. So they vary with orientation. We define beta as cot beta. Therefore, at Bragg, S of G is 0, beta is pi by 2, and hence at Bragg, beta over 2 will be pi by 4. And what we're going to predict is this. So here's the block wave excitation, right, theta I, against orientation. Here's the Bragg condition here. And so for block wave 2, for a negative deviation from Bragg, we're going to have a decreasing intensity as we go, increasing in the negative deviation. So it's going to go up like this, and this one is going to come down like this. It's going to say, okay, that the maximum excitation for block wave 1 is negative at Bragg, and it's going to decrease like that. And you might say, so what? So let's see what so what is. So consider the distribution of electrons in each of the block waves. This is kind of an interesting thing. So what we're plotting here is, here's the crystal lattice here, right? And here's our incoming electrons here, and now we've got the block waves scattered into over this crystal potential. And what turns out is that K1 here, which is the first block wave, it spends its time mainly like this. Its maximum intensity is on these atomic columns here. So what does that mean? That means our block wave 1 is spending a lot of time in the vicinity of the atomic scattering centers. So it's going to be scattered. And when we say scattered and when we say absorbed, it means that there's an objective aperture that's taking out the electrons. So spatially, our first block wave is spending a lot of time in the scattering centers. Our second block wave is spending a lot of time between the scattering centers. So we're going to say this is heavily absorbed or heavily scattered, lightly scattered. And that's the first asymmetry between these two that's very important. Why? Because the consequences of this distribution, this difference in distribution, is this. Right? The electron block wave, as I said, spend much time in the neighborhood of atomic scattering centers, so they get scattered. And block wave 2, they spend much time channeling between the atomic centers, and so they're lightly scattered. So, let's see what that means. That was the prediction for our excitations, right? At negative of Bragg, we would have block wave 1 highly excited, and block wave 2 very lightly excited, vice versa for our positive deviation from Bragg. So block wave 1, highly excited, strongly scattered. Block wave 2, highly excited, but lightly scattered. So what does the overall rocking curve look like? Because this is going to be called a rocking curve now. And it looks like this. And I showed you that before, right? We talked about so it goes like this. So do we understand that now in terms of the block waves? Here we have low intensity in our rocking curve. Why? Because our highly excited block wave is heavily scattered, because it spends its time in these centers, scattering centers. Whereas our block wave 2 over here is highly excited, but it's lightly scattered. So a lot more intensity here. And you'll notice as well that the peak in intensity is a positive deviation from the Bragg condition. Now, none of that you got from the kinematical theory. And this is something that's really important for us when we're using the microscope. Because we want, for example, if we want to see a defect, as Nestor showed, if we go positive of Bragg, we get a very bright background. And so when we scatter, we'll have a very large contrast between the scattered thing, which will be our defect, and the surrounding matrix. And that's what we want. Over here, and that's why we saw, when we were at the Bragg condition, we saw pretty grungy contrast. And as he deviated from Bragg, it got better and better, right? Because the background was, the contrast offered by the dislocations was increased because of this effect here. Now, again, I'm not a fan of all this mathematics, but I am a fan of understanding what I'm seeing. And we can understand now a lot of what we've already noted we couldn't do with the kinematical theory. So let's talk about this business of block waves spending their time in the scattering centers, say the block wave 1. So as we increase the thickness, it's going to gradually just be scattered and gone. So if you have a beating effect that gives rise to these fringes, and that's between block wave 1 and block wave 2, the reason why we run out of fringes is because block wave 1 is gone. It's been scattered as we get thicker and thicker in the foil. Right, so that's, you can immediately understand that. You can also, without, we haven't got there yet, but you can also understand wiggly images. It's going to be scattering between block wave 1 and block wave 2. But as you go to thicker and thicker parts of the foil, they start to get straight, the description, because it's only block wave 2 that's giving rise to the intensities. So it's a very useful thing to know about. These block waves are very nice because they teach us a lot about what we're looking at and how to get the best out of the best in the information. All right, how do we account for this? It's accounted for in the theory by including an imaginary component of the crystal potential. So that's this guy here. And even our physics friends have found it very difficult to actually calculate that. And so what they did was they just said, let's put in something like a tenth. Our imaginary potential will be about a tenth in magnitude of the real potential. And then they have adjusted that in the simulations of defects to come up with a reasonable number, right? So that's our imaginary potential. And that's for psi g 0, that's for psi g prime there. So it's about a tenth of the real component. And so what you'll see, and I love these profiles because these days you can do it nicely and show a nice calculated image, right? This is the old way of doing it with a profile, right? They calculate. So solid lines is bright field, this is dark field, and this is now looking at how the variation in these fringes will change. And if you look down here, you'll see the psi g thing here. So this is 0.075 there of the real component. And this is for a negative deviation, and W is here. This is the dimensionless deviation parameter, and this is about minus 0.02. So you can see that there is an important difference here between the bright field up here at the top of the foil. They're the same sign here, the fringes, and the fringes become the opposite sign. And remember, we looked at those stack and faults. We said there's on one side it was the entry side, they were the same, and then they were complementary on the bottom. So there it is. All right, and so that comes back to this point here. So let's just see if we can understand this kind of contrast. What are we seeing? We're seeing, and I'm going to show you some image, but here you can clearly see bright outermost fringe there, bright outermost fringe there, right? And dark field that corresponds to that would be this guy here, where we have a bright fringe here and a dark fringe there. So this would be the top of the foil here, the intersection of the fault with the top of the foil. This would be the intersection of the fault with the bottom of the foil. But do we understand what is actually happening in the foil, in the scattering? So here's a diagram that explains everything. So let's go through and start here. So here the electrons come in and they interact with the crystal potential, and we have a two-beam approximation, so we have two block waves, D1 and D2. By the time we get down here, all the way through here, we know they're highly scattering D1, so we only get D2, our second block wave. Right? It then sees this fault, and there's a scattering event, which we can explain in terms of the dispersion surface. We're not going to do that just right now. But this then produces D2, gets through, and it produces now D1 prime, which is like D1, a little different, but therefore we're going to get some interference effects here. Let's go over here. It looks a little more complicated, but it's still pretty easy actually. We come through D2, D1, same here. It hits the foil pretty close, so each of these is still active, and so then we get D2 prime, D2, D1, D1 prime. But by the time we get to the bottom here, D1's gone, and D1 prime's gone. And then we just get an interference between these two. Right, and it's interband scattering, it's called, and it's got these little nice sort of physicsy terms, but we don't need to worry about that right now. And then in the middle of the foil, where basically our contrast was dying out, formed D1, D2. By the time we get to the middle of the floor here, more or less D1's gone. We then scattered D1 prime, and then by the time we get to the bottom, it's just D2. So we get very little interference effects, and that's why the fringes die out. Are you starting to get convinced that the dynamical theory is worth something, right? And understanding these block waves. It's helping us understand what we're seeing and interpreting the information. Oh, and there, hence you get something that looks like this, using bright field and dark field. Okay. So, this is a computed stacking fault image profile for this particular stacking fault, and we have thickness over psi g is about 7, so it's about 7 of these fringes, and we have 0.075, so it's getting close to a tenth. And bright field, dark field lines as we saw before, right? And then this is, for that one's alpha is plus 2/3 over W. This is minus 2/3 over W, and you can see that there'll be a difference in the contrast because of this alpha here term here, which is 2 pi over 3. All right. Okay. So what they do is, just to show you what happens, our alpha is 2 pi g dot r, and we consider the problem set up as follows. Here's the incident beam top, and we say when it meets the fault, there's one set of solutions here, and they enter second, just as we saw, D1 going to D1 prime and so on, or D2 going to D1 prime. And so we have to calculate what's going to here and then continue on to the bottom. So, and I've taken this out of the book for you so you can read this. I know that you're all dying to, but basically this goes through what ends up being giving rise to these equations. I'm not going to spend time with that, but they are there if you want to read them and go through them. You can do that. What we're really interested is what's the solution here, right? So we can use equation 2420 down here on the bottom left, all right, and to calculate these two quantities. And these values are then the input for slice 2. And so it turns out that the effect of R, the displacement function, so remember the fault, second fault has a displacement vector, right, R. So it's simply to multiply the terms in CG in the lower slice by a phase factor exponential minus I alpha, and alpha is a 2 pi g R. So how do we know that? Right, remember this lovely equation here for our block waves? So we displace the crystal by this vector R, that's the stacking fault. So then our R at the end there is R minus big R, and then our block wave will look like this, or it'll look like this. You're thinking, we're getting more complicated, don't like this, but you notice we've separated out then this term here, and that is our exponential to the minus I alpha, and that's containing then this term G dot big R in it. And so that term there is the effective CG term. So what was CG? C sub G is the amplitude of this particular block wave in the diffracted beam. And so what we've done is we've modified by having the fault there, and we end up with this effective CG term. And so C naught is not affected by R, because when we have G equals 0, then of course we end up with this factor just being 0. But CG, the CGs will be multiplied by this factor here, right? So our direct beam is not being affected, but our diffracted beams are. And that's why we get this difference in between bright field, which is symmetrical, and dark field, which is asymmetrical. And as metallurgists are feeling pretty clever now, right, that we've understood these differences by using the dynamical theory, but coming out with physical ideas of what's happening. Right? We always go back to physical metallurgy. So we have physical ideas that, all right, we understand that we can see in a diffraction pattern, say, two beams. We know then they're two Bloch waves. We know that one of them is highly scattered, and so we can understand some of these fringing effects, and then as we deviate positively from Bragg, why we lose the fringing effects, and so on. So we're doing pretty well. And that is the end of the story. So, if you've got questions, Sadak will be very keen to answer them, and I will as well. But you might want to think about this, and if you're interested, you can read through the notes and get an idea. But remember, the idea in the end of the day is to have a physical feeling for understanding what you're seeing. And that's why you can't do it just by direct beam and diffracted beam. You do need to have these Bloch waves in mind and understand the interaction of them, and how Bloch wave 1 gets slowly, as you go to thicker and thicker foil, it just disappears. Which means all our wobbly images and our thickness fringes and our details on the rocking curve all gets squished out because we're losing that beating effect. So it's cool, isn't it, eh? It's really cool. It took me many years to finally step up to the dynamical theory and actually say, we need to use this. And once we did, it was great. Okay, so is it lunch break now?
Yeah.
And then afterwards we do... Nessa, are you going to lecture first, or are you going to wait till tomorrow? My advice is that you should give your lectures tomorrow, because you give yourself a nice long break in your voice to let it mend. But I can do diffraction contrast first thing. Yeah. So after lunch, get ready for an exciting lecture on diffraction contrast.